Okay. In the previous lecture, we have introduced the one-to-one correspondence between the two sets, and then we also introduced the concept of various type of the sets like a finite set, infinite set, countable set, uncountable set, and so on. This lecture is in continuation of our previous talk. Here we will discuss the few properties of countable and uncountable sets. Now, let another results in the sequence of the countable sets. Let us suppose E n and n is 1 to n so on be a sequence of countable sets and put and let S is the countable union of E n. S is the countable union of E n's, n is 1 to infinity. Then what we claim is that S is countable, then S is countable. So, a countable union of a countable set is countable, that is what this result says. Okay. Now, what is E n? E n's are given to be countable. So, it can be arranged in the form of the sequence. So, proof is since E n for each n, since E n for each n is a countable set, so its elements can be arranged in a form of the sequence. In the form of sequence, say x and k, where k is 1 to 3 and so on. K is 1 to 3. It means that is E 1 set E 1, we can arrange the form for the set E 1, we can arrange the elements like this x 1 1, x 1 2, x 1 3, x 1 4, x 1 5, x 1 6 and so on. For E 2, the elements suppose we are arranging x 2 1, x 2 2, x 2 3, x 2 4, x 2 5 and so on like this, and E n's suppose we are arranging x n 1, x n 2, x n 3, x n 4, x n 5 and so on like this. So, continue this. Okay. Now, let us consider the following array. Consider the array as mentioned above, infinite array as shown above by arrow. What is this? Suppose I take this arrow first. Let us take this another pen. Then suppose I take this as first element, this ray. Then I choose this one. Then I take this arrow. Then I take this one. X n 1, x n 2, x 3 1. Oh, sorry. This is like this. Okay. X 3 1, x 3 2. So, basically this will be the x 4 1, this is x 4, it is wrong. So, this will be x 4 1, x 4 2. So, this ray will go, okay? Not this, like this. So, if we continue this way, that is what we are doing is we are taking up this ray like this. The first element we are choosing x 1 1, the first array, then second one I am taking as x 2 1, x 2 2, x 1 2, then third ray we are taking as x 3 1, x 2 2, x 2 2, x 1 3, x 1 3, and fourth one is say x 4 1, x 3 2, and then x 2 3, and then x 1 4, like this, continue this. So, if we arrange this in the form of the sequence, then what we get is we are getting first element, second element, third element, and so on, like this. So, in this way we are getting a one to one correspondence between the elements of this set and set of positive integer. It may so happen that some of the elements of this sequence may be repeated, then what we can do is we can get the subset of this set. Since it is an infinite subset, so subset of this we can find out integers, subset of t integer j, which is also countable. So, with that it will be a one to one correspondence. We drop this common element and make the correspondence with the set of positive integer. So, if any two of them, if any two of the sets E n have elements in common, then these will appear more than once in this arrangement. In this arrangement, say star, in this arrangement star, then what we say, hence there exists, hence there is a subset of T of the set of all positive integers, T of the set of all positive integers such that S and T, which S is equivalent to T, which shows that S is at most countable. That S is at most countable. Let us see what is the meaning of this. Once we have arranged this union of this S n, E 1 E 2 n, this each E n we are arranging in the form of the sequence. So, now take the array like this. So, choose the element, first element 1 1, then second element x 2 1, third element x x 1 2, fourth element may be the x 3 1, then x here x 3 1, this will be the x 3 1, then this array where the sum is 4, Okay. So, this one and continue. So, this has a one to one correspondence with the set of positive integer. In case if suppose some elements are repeated, then what we do? We just drop that elements, take only once. So, that will be have a one to one correspondence with this subset of j, that is there will exist a subset T of the set of positive integer, which has a one to one correspond with this set of elements of S. So, S becomes countable. Okay. Now, S may be finite or may be infinite. So, but S cannot be finite. So, we can take it to be the let us why, because since E 1 which is contained in S, because S is the countable union of these E n's. So, E 1 is contained in S and E 1 is given to be infinite, and E 1 is infinite, because this is already given that sequence of countable sets E n's is the sequence of the countable sets which are infinite, of course, each element. Then E is in one infinite, then S will be infinite. So, this shows S is countable. This implies S is countable. S is countable, and that is prove the result. Okay. So, this is our okay. Same results we can generalize it. So, as a corollary we can say suppose A is at most countable, at most countable, and for every alpha belongs to A, B alpha is at most countable, which is a subset of omega, of course, at most countable. Then T, which is the countable union of B alpha when alpha belongs to A is at most countable. At most countable means either it will be finite or infinitely countable or infinitely countable. Okay. So, that is another results which we in this sequence we have. Let A be a countable set, B a countable set, and let B alpha B n V the set of all n tuples of the say A 1, A 2, A n, where A k is these h elements, they are the elements of A, k is 1, 2, say up to n, and the elements A 1, A 2 need not be, and the elements A 1, A 2, A n need not be distinct. Then B n is countable. So, what this theorem says is that if we construct a set B or V n, that is B n is the set of all n tuples A 1, A 2, A n, where A k's are in A. Now, if these coordinates of this n tuples belongs to a countable set, then this collection of all n tuples will also be a countable set. That is what he says. So, in particular, when you take n equal to 2, the ordered set of all ordered pair, where A 1, A 2 belongs to a set which is countable, then this set of for n is 2 becomes countable, and this will leads the proof for the rational number to be countable. So, let us see the proof of this first. This will be proved by induction. So, what is our B 1? For n is equal to 1, B 1 is basically only single element A 1. It means B 1 coincide with A, but A is given countable. So, once it is countable, so this implies that V 1 is countable. So, let us assume that up to B n minus 1 is countable. So, let us assume let B 1, B 2, B n minus 1 is countable set. Okay. Now, we will prove for n B n. So, consider the B n. B n, we can put it B n in the form of ordered pair B A, where what B, where B belongs to B n minus 1, a tuples where B is B 1, B 2, B n, B n minus 1 and then comma A, nth term is A. So, B 1 and n in A belongs to A. Okay. Clear? Now, if I fix B, then once you fix up B, it means each element of A, we are combining with B, that is all. So, basically you are getting A itself, is it not? So, that is nothing but, so for every fixed B, the set of pair, the set of pairs B A is equivalent to set of B A is equivalent to A, but A is given to countable, hence countable. So, thus B n is countable. Okay. Thus, B n is countable. Countable union of B n is union of a countable set, is a union of a countable set, because A is countable and this you are fixing B n minus 1, which is also a countable. So, basically B n is the union of the countable sets B n minus 1 and A. So, it is hence it is countable, by the previous result. Therefore, B n is countable. So, this proves the theorem. Now, as a particular case I told that when you fix up the n is 2, then we get the very important result that all set of rational numbers is countable. The set of all rational numbers is countable. Why? What is our rational number? The set of rational number Q is basically of the form say B by A, where A and B are integer, A is not equal to 0 and the divisor of this is 1, means they do not have a common factors in it. Okay. So, this is 1. Even if it is not 1, even if we do not put it, say 2 by 4, 1 by 2, we can take also that one. So, this is all general in this form A by B. Now, what is this? This is basically an ordered pair, say B A, where the order is a B by A. So, A is an integer, B is also an integer and both are countable set. So, basically it is a union of the countable sets. So, in the previous theorem, if we take n is equal to 2, then this shows that Q is countable, because B is in I, which is countable, A is in I, which is also countable. Therefore, it is countable. So, set of all. Now, this we will just give an example, but we will show it later. Exercise, which is we will prove it now. Set of all algebraic numbers set of all algebraic numbers is a countable set. Second, we can show we will prove that this I am leaving an example, but otherwise next we will show it also when it is okay. Set of all, that is okay. all these infinite real numbers, set of real number, or okay, set A, set A of all sequences, set A of all sequences whose elements are digits 0 and 1. All digits 0 1 is uncountable set. So, in fact, this result shows, the second example shows. So, this example shows that all these infinite set need not be countable, that all infinite sets need not be countable. In fact, we will show that set of real number is not countable. Set of rationals are countable, set of irrational becomes uncountable set. So, let us see the result, the theorem which is formed in the form of theorem, proof of solution for 2. All this you can also say in the form of theorem. As in, let us suppose E be a countable subset of this. Okay. Let given A be the set of all sequences whose elements are say whose elements are like this, all the infinite sequences, all the sequences, set of all sequences whose elements are digits 0 or 1. That is, A will be a set of this type of sequence, say 1 0 1 comma 1 0 comma 0 like this, or maybe 1 1 1 0 1 0 like this. Means all these sequences, infinite sequence where the digits are either 0 or 1. We claim that this set will be an uncountable set. So, let us suppose E be a proof. Let E be a countable subset of A. Let us suppose let E be a countable subset of A. Let us take this. Okay. It means every E can be arranged in the form of sequence. So, let E consist of the sequences, E consists of sequences, say S1, S2, Sn, S3 and so on, because this is countable. So, we can arrange the elements in the form of this. Now, each S1, S2, Sn where Si is this, maybe 1 0 1 1 0 0 0 and so on, means digits are either 0 or 1, digits 0 or 1, each Si will come. Now, from this let us construct a new sequence S. So, construct a sequence, S as follows. What is the way we are constructing sequence is that if the nth digit in Sn, if the nth digit in Sn is 1, then we let the nth digit nth digit of S V 0 and the vice versa. Means what, how we are choosing is, suppose S 1, S 2, S n is given sequence. So, I am taking constructing sequence S such that if the nth digit of S n is 1, then we will replace 1 by 0. It means, the first term of this time we will look the S 1. If the first term in S 1 is 1, we will get it 0. If first term in the S n S 1 is 0, we will take it 1. Similarly, for second term of S 2, we look the for second term of S, we look the sequence S 2 and see what is the digit. Whatever the digit there, we will take the just opposite of, means if it is 1, we will take 0, if it is 0, it is 1. It means, the sequence S so obtained will differ from all the terms of the of this construct this set E. So, obviously, so what we see here is that the sequence S differs from every member of E. In at least one place, because we are constructing in such a way. So, once it is differing from each element and E is already countable, we have arranged the term in the form of sequence S 1, S 2, S n, and since S is not coinciding with any one of the term. So, this implies that S is not an element of E. It means what? But S is what? But S is an element of what? A, because A is the collection of all such sequences whose digits is either 0 and 1. So, E is a proper subset of this. This implies E is a proper subset of A. Okay, E is a proper subset of A. Okay. And once we have already shown, and it is known, or it is shown that every countable subset of A is a proper subset of A, Every countable subset of A is a proper subset of A. This we have shown already. Every countable subset of A is a proper subset of A. So, A cannot be countable, because as soon as A is countable, then the subset which you are getting must be proper. So, this implies that A cannot be countable, because if A is countable, then here itself we are getting a contradiction, is it not? Because otherwise A would be a proper subset of itself. Otherwise, A would be a proper subset of A itself, which is absurd. Because a set cannot be a proper, a set will be a subset of itself, but cannot be a proper subset. And here, if we assume A to be a countable, then it must have a proper subset. So, this is every proper subset must be, but here we are getting that this cannot be a count. So, this shows that A is uncountable. Okay. So, this is a thing. Now, one more examples which we will deal is set of a number countable and other. Okay. Let us take the few more, that is this example as we have seen, the interval 0 1 set of real numbers is not countable. Now, this we will prove it by using the decimal expansion. Suppose I take x any element of R, we can arrange this in the form of the sequence, say x is in R, then we can write it, we can represent x in the form of in its decimal expansion. We can write the decimal expansion for this. So, if x is something alpha 1 point, say a 1, a 2, a n and so on, then this a 1, a 2, a n, and these are numbers different from 0, 8 and 9. Okay. So, in order to repeat the whole 9, and then what we do is we can construct the another numbers, say first place a 1, we can replace it by a number which is not available here. Just change it, just like a previous thing we did it. As we have constructed sequence where we have replaced the first element of the sequences by looking the S 1. If it is 1, we will take 0, if it is 0, it is 1. So, similarly, here also we looked at and then replace it by a number which is not out of this. So, that at least each element will differ from the constructed one. So, we will say it is not. I will complete this thing next time. Thank you very much.